This screencast addresses how pressure affects the boiling and freezing points of substances. So the first thing we're going to talk about is vapor pressure. If I have a beaker of water, we've got evaporation. Now evaporation can happen at any temperature, but it always happens only on the surface. Some of the particles at the surface get enough energy to escape to that vapor phase, and they would evaporate out. Now, if you have a solution, some would be condensing back down from the atmosphere, but more would be evaporating out. If we put a lid on this container, then the water molecules have nowhere to go, those that have evaporated. So they are going to escape from the surface of the liquid, and then they're going to hit the walls of the container until they lose enough energy and can no longer overcome their attractive forces. So that is going to, each time these gas molecules are banging on the walls of this container, that creates a vapor pressure. Now, if the lid is not on there, evaporation would continue and the level of the liquid would go down. Okay, so vapor pressure of a liquid in a closed container, it's called a closed system, but it's really something with a lid on it where things can't get out and things can't get in. Some of the liquid particles will vaporize, they will evaporate. These particles collide with the walls of the container and produce that vapor pressure. The model that I always use, or the prop that I use in class to explain vapor pressure, would be a water bottle. So water bottles, you are going to have, some of the particles are going to escape from that surface, and I have a better explanation here. Some of the particles here in A are going to escape from the surface of the liquid. They'll gain enough energy to escape the surface of the liquid, and then they're going to go to B here, and you've got these particles that are evaporating. They're hitting the walls of the container until they lose enough energy, and then they will condense back into the liquid. Others will begin to evaporate. Given enough time here in C, what happens is, as one condenses back into the solution, another will evaporate. And so this happens with an equal rate, and this is what we call equilibrium. So with equilibrium, we have liquid and vapor in our closed system, and we have this double-headed arrow, meaning the reaction goes in the forward direction and also in the reverse direction in equilibrium. So we have liquid evaporating into vapor, and we have vapor condensing into liquid. So that is equilibrium. We know something had to be equal about equilibrium, and what is equal are the rates. It's not going to be the amounts of vapor or liquid, but the rate at which these processes are happening is our rate of condensation, is equal to our rate of evaporation. And so we say those are in equilibrium. Now, if we again take that example of a water bottle, if you were to leave it in your car in the summertime, you're going to come back and you're going to notice that there is condensation on the inside. So if you think about that water bottle and adding heat to it, heat is going to make more of the particles move a bit faster. So more of the particles at the surface would have the ability to overcome their attractive forces. And what you're going to end up with is more will evaporate at higher temperatures. Well, in a closed bottle, you're going to have more evaporation, so you're going to have more vapor banging on the walls of the container, and that's going to create more or higher vapor pressure. Now, we use a barometer to measure the atmospheric pressure. We use a manometer to measure the vapor pressure of a liquid. So barometer is atmospheric pressure. A manometer is for vapor pressure. So it always looks here in this U-shaped tube. So you would have your gas inside this little bulb here, and over here this is open to the atmosphere. This gray part that's in the U is filled with mercury. And what we would do is measure the height difference between the two levels of mercury. If the gas is producing a greater pressure, it's going to push on this mercury and make this mercury push further down. which in turn is going to make this go up higher. And so the height would be greater between those two levels. If the atmospheric pressure is greater, what's going to happen is the atmosphere is going to push on this end of the mercury, making this level go down, and this level right here would move up, lessening the height of the mercury column. And from that, we can calculate the vapor pressure. Now, the next little statement here in number 2, the kinetic molecular theory and added heat. This is what I was talking about, adding heat to a water bottle. Adding heat is going to make those particles move faster, so it increases the kinetic energy, which is going to increase the amount of particles able to escape to that vapor phase. Since you have more vapor, this is more concentration of vapor, and that's going to increase your vapor pressure because you have more of those particles banging on the walls of the container. Now, volatile and non-volatile liquids. I wish volatile had a better meaning than it does, but volatile liquid is one that is going to evaporate easily or readily. You can use easily, that seems like a better word here. So these things are going to have very weak intermolecular forces. Substances like acetone, which is fingernail polish remover. You know if someone has been using fingernail polish remover as soon as you walk into a room. That's because as soon as you open the container, the acetone starts to evaporate, and those particles get into the air, and that is what your nose detects. Alcohol is also a volatile liquid, means it's going to evaporate very, very easily. What do you think about water? Is it going to be a volatile liquid? The answer to that is no, and the reason is because water has really strong attractive forces. Now, water does evaporate, but not a whole lot because it has those strong hydrogen bonds holding those water molecules together. Okay. Now we're going to talk about energy and boiling. If you've ever, probably no one has ever asked you to define the boiling point or what boiling is. Most people would answer that it's when the bubbles happen. And then you ask what the bubbles are made of. And the most common answer I get is air. Well, how did the air get into the liquid? So air's not quite the right answer. Boiling is when you have conversion of the liquid to a vapor, both at the surface, just like in evaporation, and within the liquid. So those bubbles are actually water vapor that has been converted from liquid water. And then they rise up and then escape into the air up above. All right, now the legal Schmiegel definition for boiling is the temperature at which the equilibrium vapor pressure of a liquid is equal to the atmospheric pressure. So we actually, in the temperature of boiling, boiling point has more to do with pressure than it has to do with temperature. So I could make a beaker of water boil on my desk without adding any heat. And just have the heat from the room. And the way I would have to accomplish that is I would need to lower the atmospheric pressure. And if I could lower it enough, which is pretty difficult to do without a very good seal, but if I could lower it enough, the water would start to boil. Now, it would not be hot. I could put my hand in it, but it would be boiling because the vapor pressure is equal to the atmospheric pressure. Temperature is almost just a consequence. So temperature is, the boiling point is very, very affected by the pressure, more so than the temperature. Now, what we have known as the boiling point of water, and we're going to use water for a lot of our examples today, the boiling point of water we know is 100 degrees C, and that's all really you have been taught. We haven't had this added layer of pressure in there. What you're actually talking about is the normal boiling point of water. When you see normal boiling point or normal freezing point. They're telling you that it is measured under standard pressure. Standard pressure is that 1 atmosphere of pressure, or 760 millimeters of mercury, or 101.3 kilopascals. That is standard pressure, and so when we talk about the normal boiling point, it is 100 degrees C at standard pressure, which is 1 atmosphere. But we don't always have 1 atmosphere of pressure. We sometimes will have less. Now, energy is going to be used to overcome the attractive forces between the molecules, and that's what's happening. It's going to use some energy to break those intermolecular forces between the molecules and let them separate and become a vapor. Now, here I have a little picture of the Earth, and you can think about the atmosphere, this column of air that's above us, as kind of surrounding the Earth almost like a blanket. And the thickness of this blanket, though, can vary depending on where you are. If I'm lying on the beach here in California, I have a lot of air up above me. And so that's a lot of air particles that are pushing down on me, creating a pressure. But if I'm over here and let's say I have climbed Mount Everest, and I'm very, very happy about this, jumping up into the air, at that point, I don't have as much air above me. And so at high elevations, my air pressure is lower, or my atmospheric pressure is lower. That's also, remember that atmospheric pressure corresponds to the boiling point. So high elevations have low atmospheric pressure, so they're also going to have a very low boiling point. In fact, on top of Mount Everest, the air pressure is about 1/3 of what it is, about 1/3 of what standard is, so 0.33 atmospheres. And water boils at 70 degrees C instead of 100 degrees C. So if you are trying to cook at high elevations, usually what you have to do is cook things longer to compensate for the lack of heat. Because when water gets to its boiling point, it's not going to get any higher, even if I put more heat to it. It is just going to boil at, like on Mount Everest, 70 degrees C. So if I'm cooking, let's say, spaghetti, instead of it taking 12 minutes like it does at 1 atmosphere of pressure back at home, on Mount Everest, I'm probably going to have to boil the spaghetti for 20 minutes because it's not getting to 100 degrees C, it's only getting to 70 degrees C, yet it is still boiling. So we're going to talk about some calculations, and this is a math component here in this chapter that'll really help us out when we start to get and talk about heat in chemical reactions or thermochemistry. And that's coming up here pretty soon. So heat of vaporization is the heat it takes to make a vapor. Now this molar means per mole. So heat of vaporization is the amount of heat needed to vaporize 1 mole of a liquid at its boiling point. So it already has to be at its boiling point. What heat of vaporization is telling us is how much energy it takes to break the rest of the attractive forces and separate those molecules so that they become a vapor. So the heat of vaporization is going to be much higher for things that have stronger intermolecular forces than things that have weaker intermolecular forces. The heat of vaporization of water. Now water has those strong hydrogen bonds, so it's really high. For 1 gram of water, now that's just 1 tiny little milliliter of water, it takes 2,260 joules of energy. Now joule is a metric unit to measured energy. We're going to get into that a whole lot here in the second 9 weeks. It's related to a calorie. In English units we use calories. That's why you'll see on your food that something is 200 calories. That's how much energy you have to expend to burn off that amount of food. Well, in metric units and SI units, we're going to use joules instead of a calorie. All right, so water's heat of vaporization is 2,260 joules per gram. Now this value is given to you, and you will have to do some calculations with water. So don't worry about memorizing this number. It will be given to you. You just have to remember when to use it. And we use heat of vaporization for vaporizing. So it's the amount of heat it would take to vaporize a gram of water. It's also the amount of heat you would need to remove to condense a gram of water. So it works for the opposite phase change. Now the equation looks like this. Q equals mHV. Q, we're going to need to get used to, because we're going to see this again. Q is heat. And I know that's weird. There's not a Q in the word heat, but we've already used H, so it's we had to come up with something, and the way to get around that is it's the quantity of heat or heat energy. And that would be measured in joules. Now, a joule sometimes can be pretty small, so if we get joules over 1,000, we're going to go ahead and convert it to kilojoules, just to be a little more realistic. M is the mass of the substance in grams, and HV is going to be your heat of vaporization. And that would be something, it would be different for every substance. You're going to be working with water, which we have the heat of vaporization. Now, this equation is given to you on your reference table. So again, you do not have to memorize the equation or the heat of vaporization of water. Both of those are given to you. This would be in a type of problem that you might have to use for this one. So it says, how much heat does it take to vaporize 11 grams of water at 373 Kelvin? Now, 373 Kelvin is 100 degrees C, and that is the boiling point of water. This temperature, we're not actually going to have to do anything with the temperature. It is just letting us know that we can use this equation, because this equation only works at the boiling point for that particular liquid. All right, so we're looking for heat, which is Q, and that is going to be M times HV. So mass is, 11 grams. Let's try that again. Times my heat of vaporization, 2,260 joules per gram. Grams cancel out, and I need 3 sig figs because the number they give me in the problem has 3 sig figs. And so that's going to be 24,900 joules. Again, joules, if it's over 1,000, then we need to go ahead and convert to kilojoules. We're going from a base unit to kilojoules, so we need to move the decimal 3 places this way. And so this is going to be 24.9 kilojoules. That is how much heat it takes for just 11 grams of water. And that's a lot. And again, that is because water has really strong attractive forces. Those hydrogen bonds are very, very strong. Now let's talk about freezing and melting. We talked about this very early on in the semester, and I think it was the first review worksheet. I asked you what the melting point of water was. And a lot of you were very, very confused until I asked, well, what's the freezing point of water? And you were 0 degrees C. Well, that's also the melting point. Freezing and melting happen at the same temperature. Freezing point is the temperature, and again, this would be normal freezing point. Normal freezing point is the temperature at which the solid and liquid are in equilibrium at that 1 atmosphere of pressure. If we were looking for the freezing point at any time, it would just be when the solid and liquid are in equilibrium. So when I have the ice and water together, it is going to be at 0 degrees C. And I have solid and liquid. Some of the particles are freezing. Some of the particles are melting. It just depends on where the energy is going after that. If I had a beaker of water here in this room, then the heat from the room is going to be adding some energy. So I would end up getting more particles that are melting than those that are freezing. And we'd start to move to total melting of that. So freezing and melting occur at the same temperature. Pressure does affect the freezing point, not as much as the boiling point though, but it does have some effect on the freezing point. Now, molar heat of fusion. So we talked about heat of vaporization. That's the heat it takes to make a vapor, or the heat you have to remove to condense something. Heat of fusion is not as straightforward. Heat of fusion is the heat it takes to melt something, or the heat you have to remove to freeze something. So again, it works for the opposite phase change as well. Now, molar just means per mole. So the amount of heat energy required to melt 1 mole of solid at its melting point. So again, this only really works when we're already at the melting point. It depends on the solid attraction of particles, because for something to melt, we have to break some of the attractive forces, not all of them. That's what we do. We break the rest of them when we get to the boiling point, but we do have to break some. So the particles can go from vibrating only to being able to move over and around one another. So the stronger the attractive forces, then the higher the heat of fusion is going to be. The heat of fusion of ice is 334 joules per gram. So 1 gram of ice will absorb 334 joules of energy in order to melt. So when we talk about putting ice into a drink, I want you to understand there's no such thing as adding cold. What happens, what makes your drink cold when you put ice in there, is that the ice uses the heat from the drink in order to melt the ice, to break some of those attractive forces. And so it is removing heat from the drink to break intermolecular forces. It can give you a headache if you think too hard about that one. Okay, the equation is going to look very, very similar. Q is still heat, M is still mass in grams, and we have to use our heat of fusion. This equation and this constant are also given to you on your reference tables. You do not have to memorize these. You have to know when to use which one. You have to know that you got to use heat of fusion for melting or freezing, and you have to use heat of vaporization for vaporizing and condensing. All right, so a type of problem that we might have with this one is how much heat energy is absorbed when 16.3 grams of ice melts. Well, we're going to be looking for Q. Q is M times HF, because we are going to be melting ice. Now, this probably should say at 0 degrees C, because it does only work at the melting point. And so the mass is 16.3 grams. And my heat of fusion of water is 334 joules per gram. Grams cancel out. All I'm left with are joules, and that makes sense for Q. I need 3 sig figs because they gave me 3 sig figs here in this number. And so I've got 5440 joules. Again, that's over 1,000, so let's go ahead and convert it to kilojoules. 1, 2, 3. So 5.44 kilojoules of heat are needed to melt that much ice. At this point, I want to show you this heating and cooling curve of water. It's a heating curve if you read it in the normal progression, and if you read it reverse, it's a cooling curve. So the scenario here would be that I have a beaker of ice. I'm going to put it on the stove. I turn on the stove, and I never touch the stove again. So constantly heat will be added as time goes by. And I'm not varying that at all. It'll be the same amount of heat that's added as I go through. So what's going to happen is that the temperature of the ice will start to increase. And it's going to go up until it hits 0 degrees C. At that point, at 0 degrees C, ice is going to begin to melt. Well, if you notice here on this graph, it flatlines. When you have, after water hits its melting point, it is going to flatline, even though I'm still adding heat. I've got water and ice, and the temperature will not go up until all of the water is, or all of the ice is converted to water. The reason for that is that the heat, instead of going to raise the temperature, is going to break some of those attractive forces. So that is where the heat is going. So ice water is always 0 degrees C. I actually use that to check thermometers. If I have a thermometer that I think isn't working well, I will get ice water, let it sit for a minute, and then I'm going to put my thermometer in there. If it doesn't read 0 degrees C, I know that something is wrong with my thermometer. Once all of the ice is converted to water, so we've finished breaking those attractive forces that can be broken at this point, and the particles can move over and around one another, then the temperature will start to go up, and I'll have just water. And it will go up until I hit 100 degrees C. Now, 100 degrees C is when water begins to boil, again, at standard pressure. And water will stay at its boiling point and will not go any higher. Even if I turn the heat up, water will not get any hotter than 100 degrees C when it is boiling, unless I add something to it. But in this case, we're just talking about pure water. So 100 degrees C is when I have water and steam. I'm still adding heat, but my temperature is not going up. The reason why is that heat is being used to break the rest of those attractive forces so the molecules can separate and become a vapor. So until all of the water is converted to steam, the temperature will stay at 100 degrees C. Once we have only steam, and if I trap that, then the temperature would go up again. Now, this is the heating curve of water, what I just described. If I read it backwards, starting with steam and going back down, it would be the amount of heat energy I would need to remove in order to get something to condense back down into water. We'll look at this a bit more. We're going to see this graph again. When you see it again, it's going to have math attached to it. We've already kind of talked about two of the places here. Let me get this writing off. Here, at this point, 100 degrees C, where it was flatlining, this is where heat of vaporization comes into play. The length of this on the graph is going to correspond to the amount of heat it takes to break the rest of those attractive forces. Over here, at this other place where it flatlined, this is going to be heat of fusion. That is the amount of heat that it's going to take to break the beginning parts of those attractive forces.